so here we go. We got hydrogen, helium. Then you got number 8. Then you got number 8. Yeah. As you see, these early elements have got isotopes, fairly stable ones, not super stable, but fairly stable below the line. That line is equal numbers of neutrons and protons. Neutrons and protons. Okay, so what do we see? See, as the elements get bigger, they leave that line altogether. Yeah. Now, the only thing holding those elements together is an excess of neutrons. Right? The old story about that, neutrons and protons. Well, it doesn't really work quite that way. Okay, so let's follow the path up. Brown is a stable. So it goes up, and then there's this weird as hell bit here. Look at that. That freaks me out. Okay, and then it carries on, but weaker, less stable, and then until there's no stable, right? So you want to find a stable version of one of these. Yeah, you want to make yourself one. It's not going to be super stable. Even if you manage to get it in this kind of like sort of area. Yeah, that's not super stable. Let's see if I can get that in focus. Probably not. Okay, it's a bit small for me to see. Hold on. Okay, I can't read that. But the ones at the top are the saber ones, and then it becomes less and less until you're looking at tiny fractions of a second down here. Okay, so what they do is they smash elements together. Right? That's what they do. And so you can see the big elements are generally the ones that they use because they're big. There needs some of them to actually impact, make your thing. But here's my issue: is that from stable to max, you've actually got fewer excess neutrons. Yeah. So the proportion of these excess neutrons to what the element requires for stability in the first place is less in proportion to the mass of the thing when you compare it to something down here. Yeah. Now imagine this, right? There's helium. That's probably oxygen there, right? You take something like oxygen, yeah, or whatever that is, carbon, right? Take carbon, for example, you get a nice big one of those, nice stable, take that stable top bubble off that, can make your sample entirely of that, yeah? It's got double the number of neutrons as it has protons. Now, when you're looking at making an element up here, you're going to need double the number of neutrons to protons. So my thing is, you need to be using these elements to make these ones. Yeah. Possibly actually using a different process. So I was thinking making them cold, so that they're less. So to try and promote the stability, make them cold, and make them under incredible pressure. So you make them cold, you squeeze the fuck up, and unnatural pressure. Yeah, right. And shockwaves, sound waves, create resonant frequencies. Whatever you can do to make actually get some interaction going. Probably been done already though. That's the trouble. Everything's been bloody done, isn't it? Anyway, yeah, that there. I did research on this. I can't remember what the elements were. Because it's difficult to draw down to get the line to find out what elements you're actually looking at. Let's use that line there. Okay, so it seems to be going from about 83 onwards. Alright, let's look at this. 83. What are we on with 83? Right, bismuth. So bismuth. And then we jump ahead. Bismuth's really stable. And then polonium, all these aren't stable. So it's the end of it's really the end of the stable elements, bismuth. That's what that is. After that, a little more rubbish. Alright. Just again to say, this book, get a copy of this book. So good. Alright. All done.